I didn't
No
notice
worries. Yeah.
that you connected already, but no problem.
Okay, so shall we start?
Just a second, I will give you a sign. So yes, please, we are now connected, we are live. Hannah, please introduce the next two speakers, next speaker, and let's try to be on time again, please.
Yeah, I'll start with the next one. So yeah, welcome back everyone after the break, and we continue the summer school with a talk of Martijn Tennekes, and he is a data visualization specialist at Statistics Netherlands, and he's especially working on spatial data visualization, and he is the developer of the TMAP package that I think many of you already know, and visualization of spatial data will also be the topic of his lecture today. So Martijn, I hand over to you.
Thank you. First of all, I cannot start my video. Is that? Oh yeah, yeah. Okay, great. Okay. Now let me share my screen. Share. Okay. So first, I'll talk a little bit about visualization of spatial data in general. It's very introductory, and after that, I'll go a little bit deeper into visualization itself, and then I will say something about TMAP. Together with Jacob, we have quite some exciting things to show. But first of all, visualization of spatial data. So, as you of course already saw, like we have like vector data, which is pretty much covered in the SF package. Well, basic types: points, lines, polygons. Of course, spatial raster data. I'll not go into depth just yet. But of course, what's already covered is the coordinates reference system, especially by Etzer this morning. The point is how, if you want to visualize spatial data, especially on a global scale, you need to think about how to peel an orange. The world is 3D, it's a globe. How to put it on a flat, two-dimensional surface or device. So that's what projected CRSs are for. We need them if we want to visualize data. I mean, we can wait a couple of decades until holograms will be common use, but until that, we have to do it with flat surfaces. Of course, so you have 3D visualization, but even like this orange, even though it's 3D, if you plot it on a flat device, it's still a 2D projection. Of course, you can use projected CRSs for visualization, but be careful because it's still a compromise. Especially when you work with global data, you need to be very careful about the poles, about the 180 degrees longitude and so on. So this is just an overview of the type of projections that we have. And some examples. That's just for record. So just skip this slide for now. For visualization purposes, doesn't matter. Yes, it does matter. So this is a quite simple example of population density. And the left-hand side map is the web Mercator, which is typically used by Google Maps, etc. And on the right-hand side, a projected CRS that was used in TMAP by default. And that's a good one for world maps. There are others like Robinson, Winkle Triple, etc. Doesn't really matter which one, but you see that that Australia is 3 times as large as Greenland, which is the truth, and not the other way around, like here. For spatial density, it really matters, because otherwise you get like a biased image of where people live. Here is you would expect that many people live in Alaska, where it's not the case. Yeah, so for statistics, that's what I mentioned here, are the properties which a projection satisfies or doesn't satisfy. Equal area, so this map projection satisfies equal area properties. So it means that the area of the polygons are basically the true areas. However, so that therefore it's still compromise. The shapes can be distorted, especially New Zealand. This is more realistic than this one. So depending on the application, so for statistics, okay, we say shape doesn't really matter because it's about population density, but for other purposes like geology, it does matter, and navigation, of course. So there we can recommend other projections. Yes, I see a question. Please go ahead, Brian. Or otherwise we can wait until after the presentation. It doesn't matter for me. For spatial data in R, there are four. Yeah, I listed here 4 core packages which are basically covered. Terra will be covered after this presentation. There's also quite handy thing in the stars package, which are data cubes, which you probably are familiar with or have seen before. It's very useful both for vector data and for raster data because you can have different layers which you can use as timestamps, for instance. So you can have a time series analysis, which you can also use to visualize. So far the basic spatial data summary in R. As for the visualization part, so now comes the core of the presentation. This is what I perceive as a good workflow for to create a nice visualization. Of course, you have to start with pre-processing of data, and data, as you know, it has like a content data part. So, for instance, employment, air quality, etc. It basically answers the question, what do we want to visualize? Whereas a spatial data component answers the question, where are those phenomena that you want to visualize? So you need to pre-process, like taking into account missing values, duplicated values, all those things. After that, you join those data, and then you can start the visualization part. And that's also these 2 blocks where TMap comes into play. And other packages as well, of course. But yeah, I'll just cover things that are in TMap after this, the slides. And this basically, so in this block, it's about data-driven spatial transformation. It's an optional block. Not many visualizations have those transformations. However, it will become optional in TMap in the next update. And I'll explain what this is. So when we have spatial data, you can use the content data to change the features. You can, for instance, inflate polygons or deflate polygons, as I will show in the next example. And for that, you need like a variable of interest, some scaling function which scales to the size of polygons, and then apply a certain data-driven spatial transformation. After that, you have like this transformed data that still contains a content part and a spatial data part. And then you need a visual mapping. So this means that you need to map the data variables to the visual variables. Now the visual variables are, these are the most important ones. So colors, well, I have multiple different type of color palettes, size, shape, Others are alpha transparency, line type, fill pattern, etc. Those are a little bit less common. They're not included into TMAP yet, but they will be. I'll talk about that in a second. And then, yeah, here's our spatial object types. So symbols, lines, polygons, and rasters. So basically, you can map a variable to either color palette or symbol size, symbol shape, line width. So line width is basically size, basically this one. And when you have done that, yeah, you can just plot it on a map. And it can be static map, interactive map, etc. That's up to the device, but at least you have the information to create the visualization. So an example of this data-driven transformation function is the Cartogram. So you've probably seen it. It's a little bit playful way to visualize, in this case, Happy Planet Index corrected by population density. So what we do here is we distort the polygons such that the areas correspond to population size, and such as neighboring polygons still touch each other. There's also a non-contiguous variant of the cartogram, which polygons just shrink but don't touch each other. In this example, so I used population as a data variable, which I mapped to polygon size as the weights. So population is between 0 and 1 billion, and I use a continuous scale to scale it to 0, 1 units, weights in this case, which then are passed on to the cartogram function. And then I use Happy Planet indicator index. So these numbers are between 10 and 45, but I use intervals because, well, you can use continuous color palette as well, but in this case I choose intervals, which has the advantage that you can really read the value better than a continuous color palette. But these are choices. These are choices that depend on the task, on the user, background of the user, all those things. So in this case, I use a diverging palette, red, yellow, green. This looks pretty nice. However, I've been told that this color palette does not work very well for colorblind people. So therefore, in the next major TMAP update, we switch to another default. We haven't decided which one, but at least we want to take into account those people because there are many of them. So this goes a little deeper into visualization itself. So visualization is all about losing information. We often want to visualize all information because you don't want to lose any information. Maybe it's important, so we're really afraid of losing information. However, big data, spatial data in general is often very detailed. And for many user tasks, this high level of detail is not needed. So if you want to visualize for instance, like climate change on a global scale, you don't need to know that some kind of neighborhood in some city had like a very high temperature at some point of the day, just to give an example. Then it's probably better to use some kind of kernel density smoothing to visualize the global patterns. So information loss is therefore key concept in good visual design. You can think about how to lose some information, but on the same side the other side of the same coin is the goal of visual design is to find the best way to depict some information. So that's basically, the question is, what information do you want to visualize? It's the same question as what information could you get rid of? So for instance, the underground map. So the question, is realistic always better? So the underground map is not realistic. So these are realistic locations. However, often people find these maps to be very useful. Why is that? Because of the population density. The population density in London city center is much higher. Therefore, the metro stops are closer to each other, and as a result, you can print the labels better. You need very small font size. Also, the directions here. Okay, here we also use like 8 cardinal directions. In reality, it's much more organic, I would say. But due to this schematic way of visualization, it's easier, to digest this load of information. So you need to think about. So this is also, maybe it's also a case of data-driven spatial information, where you use population density to move the points, the underground stops in this case, a little bit farther from each other in order to be useful for public transport planning. So we use this. So these concepts of information loss are borrowed from information theory. And I've been in Oxford for half a year, and then I worked together with Professor Min Chen, and we focused on a design space for origin destination data visualization. So here's the reference. And in this case, we composed 4 dimensions. So this design space consists of 4 dimensions, and the first 2 dimensions cover like the data structure of the nodes and edges, and third and fourth the visual variables. So basically, how to depict them. This is just an example of applying these concepts of information loss to a specific type of spatial data, namely origin destination data visualization. And when we worked on that, we kind of saw a new design emerging, because I had this data set of Dutch commuting, which basically described how many people commuted from one municipality to the other. And eventually we designed this map. So it's called the donut map. Let me show you. Let's see. It's here. So I can put the URL in the chat to everyone. There you go. It may be a little bit slow because of the Zoom link, but well, it's okay. So what we basically did is instead of whole lines, so we draw half lines. This means that the flows between Utrecht and Amsterdam can be depicted by 2 half lines, which together form a whole line. I've been told that's also Gestalt theory, that's the underlying core principles behind it. In this case, the pink lines are the commuting flows of people who work in Amsterdam, and the green ones who work in Utrecht. And the donuts summarize where the people who live in Amsterdam work, and the majority work also in Amsterdam. And you can see the commuting towns where they work. So a lot of commuter towns have people who work in Amsterdam because of these pink parts. Many people here work in The Hague, so it's a little bit trivial, but and the interesting thing is for policymakers, it can be really interesting because they can find out whether it's about the number of jobs that's available because so many people commute, or because it has a good public transport system, or on the other hand, not so good. So they can like create infrastructure based on these data. So back to the presentation again. So visualization of spatial data in R. This is kind of an overview. It's probably not complete, but as far as I know, these are all great packages to visualize spatial data. Well, the plot function is fast and straightforward, so it's implemented in every like class package, SF stars, Terra, etc. Usually is the fastest way to plot data. ggplot2, it's really great. In the past, it was a little bit lagging behind because it's not suited for spatial data, but today it is. So TMap, yeah, we started, I think, a couple of years ago, 6 years ago, and it's maturing. It's mature right now, and currently we are, as I will talk in the next slide, have plans for a major update. MapView package is also really great. So both TMap and MapView are built on top of Leaflet. So Leaflet is used, it's a JavaScript library for interactive maps. And so TMap has two kind of modes, two devices. So the static device, which you see in RStudio, and the plot device, the view device, view pane, in which you can see interactive maps. And these interactive maps, we are using Leaflet as a fundamental package for that. MapSF also looks really nice. Haven't used it before, but very promising. But now about TMap. This is the news I want to share. So as I said, the current version is pretty stable, pretty mature. Of course, there can be bugs anytime, as with any software. But it's kind of grown to its full potential. However, we had trouble in extending it. So therefore, we had to develop a new framework. So for the user, a little bit, some things will change, but the core concepts will, of course, be the same. But it can be much easier. It will be much easier to extend it. And the next news I want to share is that we are going to publish a book. So me and Jacob Novstad. The draft version is already online. It's over here. And it basically covers, so we completed about half of it, probably a little bit more, but at least the fundamental things that you need for TMap. Spatial data in R, this more general, TMap in a nutshell. It's really, if you want a quick overview what TMap does, you can read this chapter. Basically, you can go through it very briefly, just an eye overview. QTM, so if you have a spatial data object, no matter what class, you can plot it with quick thematic map. In this case, volcanoes. Let me close my email for a second. Okay. And so if you plot it in the TMap way, which is, if you're familiar with ggplot, kind of similar, but it has some things that's done a little bit differently. So what's instead of ggplot dataset and then the aesthetics, we use TM shape. So TM shape is used to like specify what I call a shape object. It's a spatial object, it can be an SF data frame, stars object, Terra, all those things. And then we have like the map layers. So these are TM symbols, TM polygons, lines, and TM raster. These are the basic ones. TM text. And then you can specify aesthetics, which means the visual variables. And this TM symbol has 3: color, shape, size. In this case, we keep the shape constant and we use a data variable to be mapped to the size visual variable. In this case, so elevation. Elevation comes from volcanoes, and we have a title. Let's see if this map is there. This is this map. So apparently 24 is triangles and elevation is used. So here's a legend. It's scaled to elevation. And so on and so forth. So yeah, as you can see here, you can design the map any way you want. So like background colors, you use a continuous scale for elevation. So it's supposed to be a really flexible package. So here's some map attributes like scale bar, compass, etc. See how much I'm on time. Okay. Yeah, so I said we have the plot and view mode. So I can show little quick demo. So I have the world data set, so data world. And if I go TM shape world, TM polygons HPI, I have the happy planet index. And if I use, let's do it here, team map mode, view, and then I can rerun this code, and then I'm in view mode. That means interactive mode. This all thanks to Leaflet, the people who contributed to Leaflet, what made it possible. Again, for statistical mapping, it's not really great because what I said earlier, Greenland is still 3 times as large as Australia. But other than that, it's very neat that you can zoom in and zoom out. And so back to the book again. Yeah, not all paragraphs have been written yet, but I think the core is there. So in this book, we'll cover like how to specify spatial data, like with the TM shape function. The chapter 5 is about layers. So these are the base layers and the derived layers. These are the visual variables you can use, and the geometry that it expects, which means that it can take more geometry. So for instance, TM polygons can also take TM the way around. TM symbols can also take polygons. Then just the centroid is taken. And if you, for instance, use multiple shapes in multiple projections, then it's automatically, so this is all described by the way in the previous chapter, then it uses the CRS of one shape, which you can later on change. So chapter 5, chapter 5 was about layers. Chapter 6 about visual variables. You've seen this picture before. To dive a little bit deeper. Yes, so other types, so these are not written yet, so layout is written, it's already finished. So you can use different font size, etc. So please let me know if there are any questions or suggestions. We're open to that. As I mentioned in the slide, so this book is written for TMAP 3. and will be updated to TMF4 because there are quite some changes in TMF4, which I want to present now. So TMF4, the major thing is that it will be extendable. And it's extendable in many ways. We can add map layers, or by we I mean developers, other than me, who wrote basically the framework of TMap, but anyone who is familiar into R can add map layers. You can think about TM donuts, like the donut map that I showed, TM hexagons, TM network. So for instance, if you have like an SF networks object and you want to visualize it straight away, why not use TM network? We have to, of course, think about how to use it and what kind of aesthetics you have, etc. But sky's the limit in this case. TM hillshade. There could be many more, like TM kernel density estimation. Aesthetics, so there will be many more visual variables available. So we have added 5 new aesthetics for TM polygons. And again, it will be relatively easy for developers to add new visual variables. Once you have like a method to plot them, it's also easy to add them. So the graphics engine, so TM3 had 2 plot modes. Plot, which basically is built upon the grid graphic system, and view, built upon leaflet. But if there is another plotting mechanism, graphics engine that could be used, why not use it? And finally, spatial class we use is built upon SF and stars, but it will be also more easy to incorporate other classes as well. So for instance, the Terra classes. So a small example of the aesthetics. So just to show the pictures, it's easier. So this was basically, about syntax. So the syntax will change too, because there are many arguments. If you look at TM symbols, for instance, they are like a huge list because we have 3 aesthetics, and every aesthetic has a bunch of arguments. In TMF4, it will be organized in this way that an aesthetic still is an aesthetic fill. The scaling arguments are bundled into a scale function, in this case TM scale intervals, and the things that only are related to legend is configured in TM legend. So for instance, the title. This is an example of 3 different aesthetics. So we use, as you can see, I've improved the continuous legend here. Still have to implement the landscape legend, but so border width and line type. So in this case, border type is life expectancy. So dashed means a little bit earlier in life, unfortunately, thicker. Or no, the solid lines means a little bit later. Well-being, thickness of the lines, and happy planet index is color. So in this case, best to live in Middle and South America. Map layers. So the cartogram that you already saw. And this, by the way, is an example of a diverging color palette which takes into account color blindness. So it's used as a transformation aesthetic. So it's basically distorts the polygons such as the areas correspond to the number of people who live in the countries. The code is here. I'll not go into detail. You can see again the aesthetics remain the same, and the scale arguments are bundled in the scale functions. And skill functions are summarized over here. So I currently have these ones. Doesn't mean it changes, but can mean we probably we add a couple of more. So for instance, date, time are not included yet, but I will include them. These are the main data types that are expected. So, and you see the differences in this map. So it's the Happy Planet Index or life expectancy. Let's check life expectancy in Africa using 6 different scales. Categorical, every unique value has its own color, and the colors are repeated because we don't have enough colors. Not very useful in this case. Intervals, very useful, because you have a sequential palette. And you can really read the categories. So this orange is this one, 60 to 65. A log scale for this type of data is not very useful. Could be useful for population density or for income, economic data, but not for life expectancy. TM scale ordinal is also a categorical variant. So this is class vector, this is class ordered. Also here every unique value has its own value, but it's also not very useful because this scale is not equidistant. So for instance 53 is missing. And so the continuous scale is also very useful. It gives a better image than this one. But the values are a little bit more difficult to read from the legend. So these have pros and cons, but these are both very useful. TM scale discrete, this is new in TMAP. It basically has a discrete numeric scale. In this case, I'm not sure how valuable it is because there are many values, but if you have like 5 or 6 values and there is one missing, then you still have an equidistant scale. So this will be very useful for that. Multivariate scales. So we can, for an aesthetic, we can assign multiple variables. So in this case, I have a bivariate choropleth. I still have to design the legend, but this is like a concept. In this case, we have like 3 classes: well-being and footprint. And you see that, for instance, North America has a high footprint and a high well-being, whereas Europe, medium footprint, high well-being. So it's pretty easy to read the values, and you have like a bivariate choropleth. In TMAP 4, the way it's implemented is by using this MV, stands for multivariate. If you have suggestions for other function name, please let me know. But I want to keep it short and tidy. So for now, I've called it MV. So the first variable which defines the rows is well-being. The second, footprint. I have a scale, TM scale bivariate. And I can, for both the rows and columns, assign a scale function, in this case intervals. And the values are a bivariate color palette. I'll talk about color palettes a little bit later. For now, so this the donut map that I showed, it's not, so this one is not implemented yet, but it probably will implement it like this. This one is also not implemented, and I'm not sure exactly how to create this map. And also not know what kind of extension libraries we're going to make for that. But I think using SF would be great. And like this, for instance, TM shape edges, or maybe TM shape network, and then TM half lines, TM donuts, and here again, so size, it corresponds to the number of employees who live in the specific municipality. And the parts, the donuts, is also a multivariate thing. It's basically a symbol. And the content of the symbol is donut chart, and we need to have the number of employees who work in the highlighted municipalities in this case. So it's again an MV function. A legend, so the legend positioning will be different. Will be more options to keep them both inside, outside the map. You can specify it per aesthetic. So each aesthetic will have its own legend argument, which you can specify in different ways. In all team map, all legends need to go into one position. Also, what's also new is, let's see, this is not sure what I was going to show here. Oh yeah, we'll also have like shortcuts like TM place legends left. So I plan to, so the options will be a little bit more complex because the framework is more complex. But we plan to have like a couple of like magic functions that does it all in one function call. And the nice thing about TMap 4 is that, let me show that, is that you can use auto-completion for that. So if you do TM place legends, then you can just place them right. And then you have just to specify the width, 0.2. Let me see if this works. Yeah, it works. So etc. So yeah, those things are really useful. Again, so this is really development version. A lot of things don't work yet. If it will be more mature, I will ask you, all of you, to give us feedback of what kind of functions you need. Are the argument names intuitive, etc. So it's also new. I've had this question a couple of times, whether people could make this kind of legend. So we use two aesthetics, symbol size and symbol color, and one legend. So basically, the same data variable is mapped to two visual variables. And now we can say TM legend combine. So the size legend will be combined with fill legend. And one of the last things I want to show this a little bit more. So there is like a free argument, which decides whether facets, the scales of the legends are free, so per facet, or shared among facets. What's new is that can also be done for a facet grid per row, per column. So this is kind of a theoretical example. Let me see, what do we have here? Income group over here. The rows and the columns is economy. Life expectancy for the fill, it's determined per column. So therefore columns is true. And I have the legends for the red symbols, and red symbols are GDP, and it's determined per row. So yeah, that's a new feature. I'm not sure how much it gets used, but at least it's there. So for the backwards compatibility, yeah, it will be backwards compatible. The options will be different because for instance, we want to take into account colorblind people, etc. However, there will be a style called, as I see it now, TMap v3, which reverts everything to the current set of options. So the color palettes. So let me show that here. So I have a function. It's basically the comparable to the palette explorer, which was in TMap tools. Fortunately, I'm on Windows, so installation gets a little bit quicker. Okay. It just renders a large PNG and opens it in a viewer, so you can browse through the palettes. What I plan to use is have it as an HTML format so that you can copy paste the palette names, because they could be very long. But as you see, so we've not decided how to organize these. So far, it's been organized as categorical palettes, sequential palettes, diverging palettes, and cyclic palettes, bivariate palettes. And you see here the family. So I have like the Covesi, Carto, Brewer palettes, Ocean, HCl. So both HCl and let me start at the beginning. Yeah, HCl palettes are base R packages palettes. We still haven't decided on the default, but yeah, I think that's all I wanted to show. Let me see. Yeah, so suggestions are welcome. So we have the GitHub page. There's this yellow tmap v4 sign tag that you can use.
Yeah, we have a lot of questions.
Yeah. Okay.
And it's just yeah, it's a good time to stop. So Hannah, please.
Yeah, all right. Thanks a lot, Martijn. I collected the questions on MetaMost, and
there's a lot of questions. So Martijn, please just try to go fast.
Exactly, and the questions that I will not be able to answer, I will answer online.
Yeah, great. So the first question is, can you please reflect on geemap.org? That's a question from Tom. And how can our community catch up with cloud-based solutions to visualize data?
Say again, Joy?
Or maybe Tom wants to ask the question.
They made a package to work with Google Earth.
Yeah,
it's called GEMap. So how do we catch up with that? Because you can visualize also really large data sets. And
yeah, I think it has both pros and cons. I mean, the great thing is about the R Spatial community is that everything is open source, everything is connected, everything is possible. How do we catch up? I don't know. Maybe we can kind of have an interface to that. So I've seen it, but not used it myself. So
okay,
that's a good question. Yeah.
Okay. The second question: would you say TM shape is suitable for plotting high-resolution data as well, or is it recommended always to aggregate data before using TMap?
That's a very good point. There's in TMap shape. Let's see how I go. Probably there's something in the. So there are a couple of options. So data simplification. We have a simplify argument, which you can set to simplify polygons. For rasters, we can. I'm not sure if it's in this chapter, but we have like a max raster option, which is set to say I think 1 million. Which automatically downsamples spatial rasters because you cannot really see more pixels on that. So it's basically done automatically. And I have to say, in stars, it's really fast. So yes.
Okay, then probably a related question: does TMap also handle the use of satellite images as base maps?
Yes. So that's a good one. It should be. It should be. So we can, of course, use that as if there's a tile server of satellite images, we can use it, of course. Yeah, then we can use this base map. So I still have to implement base maps for static, or for the plot mode, because it's not there yet. You still have to use, for instance, map tiles to download the tiles or satellite images, and then you can use TM raster, TM RGB, but it's better, yeah, to have it as a base layer.
Right. Next question: can TMap be used to export to KML to be opened in Google Earth or similar?
It's a good question. I've also asked the question one time, whereas the maps can be exported to ArcGIS, for instance. It's a little bit harder, I guess. For KML, I can imagine that it's possible. And that's not too hard, but it depends on the map. I mean, if you have like a really complex map, then it's a little bit harder, I think, to create an export
But
function.
you can always make a PNG as a ground overlay, and just put it.
That's always possible,
yeah,
exactly.
But
That's always possible.
That would be pity to lose the vector structures, So
yeah. You can probably also export it to SVG, which even more, even better.
Okay, and next question is from Gerard. Do you want to ask it yourself or shall I read it?
You can do that, Hannah.
Okay, so the question is, wait, no, I have to split it, yeah. Do you have any experience with visualization of uncertainty in spatial data?
I've thought about it, but not. It's a really interesting one. You can map uncertainty to a visual variable. So say alpha transparency. As you have to be careful about the color palette. But if the color palette is, for instance, one from Viridis, so let's take one, which falls, for instance, this one, or the HCL palettes, which have same brightness, more or less, and then you can use alpha transparency to decode uncertainty. So the brighter the color, the more uncertainty there is. That could be an idea, but I think it's also depending on the use case.
Yeah, thank you, Martijn. I think Tom did something similar in the past with a whiteness blurring or something like that.
Okay. Yeah, that's kind of similar indeed. Yeah, maybe you can also use the line type. So what I showed in the vignette. Is the vignette here? Something like this that you kind of, I'm not sure yet. There's also a nice one. The City University of London, they create sketchy graphics. If you have like a polygon, you can use the exact borders, but you can also like sketch it a little bit. Also indicates. So they use it, for instance, for bar charts. If like preliminary results. Then you can just sketch a bar chart as if it's written by pencil. Maybe that could be used as well.
All right. Currently, the last question on Overleaf is if you can add something like histograms of classes or values into the legend of TMAP. There's an example of how that should look like included in MetaMost.
Yes, there's a TMAP. Let me use Google for that. It was possible on TMAP 3. So there was like, for instance, this one. At the time, a couple of years ago, I just made like this histogram. For TMAP 4, we have to think about it because I want it to be general as possible. But for sure, we plan to do that. And not just histograms, just any chart which can aid the analysis. And also, I've also asked the question, whether it could be possible if you have like an interactive map, if you zoom on it, you can show it. Ideally, you want to show it in the pop-up. In many cases, it will be useful.
Okay, good. And thanks a lot, Martijn.
Okay, you're welcome.
Lecture. And I think we're just in time to move on to the last speaker of today before we end the summer school with a panel discussion. Robert, are you there?
I'm here.
You can stop sharing, Martijn.
Yes, I'm looking for the button. Yeah. Just stop. Stop share. Yeah. Okay.
Okay, good. Then we continue with the last session. And I quickly like to introduce Robert Heimans. And Robert Heimans is a professor in the Department of Environmental Science and Policy at the University of California in Davis. And he is working on spatial data analysis in biodiversity, agriculture, and health science. And he is the author of many R packages, for example, Raster and Terra. So, Robert, please go ahead. I'm looking much forward to your presentation.
I hope it's not too early. I hope it's not too early in California.
I would have to think about that because that's not where I am.
Okay.
But, so it's 4:15 where I am, and that's the same as where you are. I think I would show my face, but the host doesn't allow me to. So you can look at my Starbucks drink. Not that you miss much, but
I think now you can. But
let's see. I cannot.
Okay, then I think Tom or Valentina, you have to change.
But can you see my screen though?
Yeah, we see a screen.
Well, then
we see the first slide. Yes.
We'll just go with that then.
Yeah,
so yeah, hello. Thank you, Anna, for introducing me. I'm Robert Heimans. I'm going to speak mostly about the new Terra package, which is a very general spatial data analysis package. And so thinking about how to couch what I could say about it, I thought, well, let's talk about it in the context of reproducible workflows. And the reason that I thought about that is twofold. One, I was thinking like, well, what made me start working on R and developing R software? And the most important, the two really important considerations. One, I wanted the freedom to do the data analysis that I want to do without any software vendor sort of telling me what I could do or could not do, but also without having to reinvent the wheel. I used to write software from scratch, and within R, of course, I could build on stand on the shoulders of giants. But the other big thing was reproducibility, especially in collaborations when people would sometimes come up with results that I look at, they're like, what? Very difficult to really have good trust in results if you cannot look at code and see how it was derived. And then thirdly, later on, as I moved to the teaching job, also for teaching and thinking about how to make relatively complex workflows as simple as possible so that users of this kind of software can focus on what they're really interested in with a minimal basic knowledge of coding that you will need, but without being drawn into very esoteric code writing. So I'll first give a very brief introduction of the Terra package, and then I will show its use through a case study that I also gave out as a challenge question, which was really more a challenge project. It was it was clearly a bit much to ask for, but I wanted to challenge people to think not only about reproducing something, but also about validity, reproducibility, and validity. Going perhaps a bit beyond sort of what was the topic yesterday about cross-validation and just a number, which obviously is very important and dear to my heart. But there's much more to thinking about valid research. All right, so my context is spatial data science, and I thought let's define it so we know what I'm talking about. And I highlight these red words. So spatial data scientists, which many of us now are, I think, and I assume many of you in the audience are or maybe aspire to become. We write code, so that's crucial to create reproducible workflows, not one-off things, but we can show where results came from, and we can build on it and reuse it. To often analyze complex data, and to me, complexity is really the key here. Often people talk about big data, that's a part of it, but really where it gets interesting and difficult is the complexity, putting different types of data together and making sense out of it. Using appropriate analytical methods, guided by domain knowledge. These methods is also, really something I hammer on a lot in my teaching. in a sense, I feel, people tend to find hammers and see nails everywhere. People doing spatial data analysis tend to often come through sort of GIS paths and have pretty limited statistical background knowledge, but then they want to jump into this other kind of spatial modeling. It doesn't always work well. What you really want to have is some domain knowledge, some understanding of process before you necessarily jump into analyzing data. And so being a good spatial data scientist then is a really hard task. You need to have a whole set of different skills to do it well. And so I think that is, to me, a challenge, and that I think to many of you will be a challenge as well. And I'm going to talk a bit about reproducibility, in part also because I feel I need to start talking more about it to educate my students, but also myself, because still today, every time I write a paper and the paper is done, and I want to write in the appendix or or somewhere like, well, you can reproduce this with this code on GitHub or so, I feel like, oh well, actually it's not so easy. There's maybe partly. So I think it's really important that we talk more about that. We often talk about data sharing, but very little about sharing code and thinking about what are appropriate workflows for complex data analytical problems. So again, I won't go into a huge depth of any of this throughout this 1 hour I have, given the different things I want to touch upon. But I think that's sort of the general broad stage, or topic on the layout that we maybe can discuss it now, maybe also during the forum later. And I think it's just important to get this conversation going. And maybe some of this has happened during these couple of days. I unfortunately haven't been able to be in much of it. Okay, so first let's talk about Terra. So Terra is in some way similar to SF in the sense that it replaces sort of old school spatial data in R. Terra, especially the raster data, but really both raster and Terra, have both raster and vector data support. In fact, raster did also, the raster package did a lot of vector manipulation building on RGOs. So the old school raster data analysis was raster, RGO, SP, RGOs, that's the F4, those packages. Lots of that has now been put into this new Terra package. Why? Well, raster had many good things, I believe. I thought it was relatively easy to use. It was, had a lot of functions you could use. One of the innovations at the time was there were no file size restrictions. So, you didn't have to load all your data into memory to be able to work with, say, large amounts of satellite data. It was also unnecessarily complex. And I was kind of interested in hearing Martijn speak about TMAP. And I mentioned something similar may have happened. You start writing a package and there's a lot of path dependency. I started first with this raster layer idea, and then I thought, oh, we should also have a stack. But what about this case? That should be something else. And before you know it, you have all these different functions and objects or classes that really could have been designed in a much more simpler way with hindsight. And so, with that hindsight, I started working on Terra a couple of years ago. And there were some ugly things as well, like, certain file formats not supported and certain functions much too slow. So Terra came out a year and a half ago now. It's very much like raster. It's simpler. It's generally faster. Actually, not always, not everywhere, but most cases. And it's much better in many small ways. Complex to point out all these small ways, but I think it really works much better. Except that it's still a new package, so there are still some bugs that people are finding, and thank you all very much for doing that. But I'm quite confident to say that this is stop using raster, start using Terra, and if you get stuck, let me know, and I'll make sure that Terra can do what you need to do. Just one more technical slide, sort of like, okay, how is Terra also different sort of under the hood from raster? So raster, like most R packages or many R packages anyway, are mostly written in R. Terra, however, is almost the opposite. It's almost entirely written in C, C++, or in C++ really, with some C libraries. And so essentially there's this, what I call the SPAT library that does all the work, that uses GDAL and GDOF and NetCDF libraries. And then there's this RCPP module. There's this thin wrapper, you could call it. There's this interface between R and C++. And so that allows you to use it through R. But the nice thing about this design is what, I designed this way for speed in part, but also I sort of didn't want to pollute it, if I may, with sort of RCPP code, such that I can also essentially compile as a standalone program. And on the long run, I want to make a very similar package using Boost module in Python, where you would have exactly the same interface in R as in Python. For most of you, this doesn't matter as end users, but this is it has one big implication, is that I try to not build too much on, or at all, if I can, on other R packages, because I don't want a dependency. I want to have the standalone C++ software that I can use in different contexts. If you want to learn about using Terra, this is where I would send you, rspatial.org/Terra. There's a similar version for the raster package, as some of you may have seen in the past. It's nearly complete now in terms of a copy of what was available for raster. And when it becomes complete, there actually, I got plenty of plans for much more. But that's where I would start. So a final slide on Terra. I think it's currently getting quite stable. There was a peak in development still early this year, and then a peak in bugs over the past months. Now it seems to have slowed down a bit, but surely there are still issues to be found. So please, if you find them, you make a huge contribution by reporting them. I've very frequently I've met people say, "Oh yeah, I found this thing that didn't work," but they never told me. It's like, well, if you'd only told me, you would only have helped yourself, but you would also have helped so many other people. So if you want to make a small contribution, providing bug reports or even simple feature requests is tremendously helpful. All right, so now I want to jump into the case study, and through that case study, just will show Terra in action. And I took this case study because it's one of a few papers that I've been working on to reproduce and to write a bit about and to have some thoughts about that. The highlighted red area summarizes essentially the finding that they find that they say there's two groups of religious beliefs. Ones that have high moralizing gods that basically are moral authority that tell you what is right and what's wrong, and other religions do not have that. And they find that those beliefs tend to be more common in more poor environments. So just to be sure here, I'm not making any statement about religious beliefs or about your religious beliefs or about any like that. I'm just sitting here, imagine myself being some intelligent being from another planet, looking at planet Earth and just seeing, well, what kind of patterns do I see here? So please, if you have religious beliefs yourself, keep in mind that it's with that distance that we look at this. So I hope that some of you have looked at the paper and have tried to reproduce some things. And the first thing that I did was making a map. But before that, I have another general slide here, which again, it was a bit of my motivation here. This is a paper I use a lot in teaching. Why most published research findings are false, and partly I use it because, of course, it's a beautiful paradox. But also, I think it's really important to think about it. Now, this paper goes, it's much more about sort of type 2 statistical inference errors and things like that, beyond sort of what I'll be talking about. But it's very clear that a lot of findings are incorrect, and it's really interesting to think about why that may be and what we can do about that and how that can help your writing or your reviewing. And this could be one of these cases. So let's have a look. Well, first I started out with, as I wanted to say earlier, let's just get the data in and reproduce what we see. There's a couple of figures in the paper, and I'll just only show this map. Of course, I'll focus a bit on the spatial data. So they have a map of where and where not do we see these particular religions, so to believe in moralizing high gods, and an underlying map of net primary productivity. So let's go to our studio, to my first script. And I start out with making this map of net primary productivity. So I use the Terra package, and I use the geodata package that just allows easy access to spatial data. I have a function here, which is NPP, based on this PDF here, which actually is interesting. It's quite a challenge if you read the PDF to even to derive what this function should be. The differentiation between mathematical notation and code is, it's entire, or the step to go from mathematical notation to code and vice versa, can be really challenging. I think science still works on the notion that mathematical notation is king, right? That is, if you can write this, then you really are a scientist. The problem, however, is that, this is how we implement things or tend to implement things. And in many ways, this is what we really need to understand what's going on or something like this. Now, of course, there's the issue with, this is R, what if you want to use Python or C++? But even then, I would say, particularly with a simple function like this, it hardly matters. But anyway, suffice to say at this point, it was a challenge to translate that. But I made this function. I downloaded precipitation data. So if I do prac, I can look at that. Oh, that's actually not great here in the big font. So prac is a spat raster. It has, rows, columns, a number of layers, 12 layers, one for each month. 12 sources, because each month is a separate file. Min and max values for each of the layers. If you ever used raster package, you're familiar with this. I want the annual precipitation, so I have the overloaded sum function. I say, well, sum this up, and you can always wonder, of course, what does this do? What if now we have these 12 rasters, and I could plot them. I have to go back to the original to do that. Plot prac. Plot prac. So we have, it takes a little while. We have these 12 layers of monthly precipitation. So one design question in Terra, of course, is, well, what would sum represent? Sum could be just a sum of all values. But it could also be the sum across cells of each layer. And that is the general design principle. There are, of course, ways to sum all values as well, using the global function. But generally, raster is, we want to keep, maintain sort of the raster structure. So by summing, I can type. We now have annual precipitation for the world on a raster cell. So a similar thing for average temperature. There I take the mean. Now I want to have them together in a single object. So I use the C function, combine, just like a normal R. In raster, it used to be stack. And so now I have the clim object. It has 2 layers. One is called mean, the other one is called sum. That's not great, but that's because, one was the sum, one was the mean. So let's do maybe names prac is, you could call it precipitation. I'm too lazy for writing out long names like that. So I'll just do that. Assign those names, do this again. Okay, now we have names that are more easily to understand. We have Antarctica in here. That was not part of their map. There's no people living there, so there's no religions that we know of, unless the penguins do, that's something we don't know about. So let's crop out by -180 to 180. So east to west, and -60 is sort of, you know, around here. Let's cut out Antarctica. Okay, and so now I have the input variables to this function to compute the net primary productivity. And now the question is, how do I apply that? There would be two ways. You could actually you could write this function in a way that the rasters would be an argument, but more typically, and generally a better approach is to write first a function that works on a vector, and then apply that to the rasters in one way using one of the several apply family functions. Well, one thing I see go wrong a lot is that, you know, somebody will write a function and they use it. In this case, you want to use lap without checking the function first. So what you want to do always is something like, well, let's check the function. So let's say 10 degrees and 100 millimeters, and we see, okay, 192. I forget actually what is it, gram per square meter. Well, I don't know what the function, what the unit is, but let's think, well, if it gets warmer and wetter, we should get at least more per. Oop, that was not what I wanted to do. I don't know what I did there. It should get, you should get a higher productivity. Wetter. High productivity. Clearly, your rainfall was limiting at 100 millimeters. That makes sense. Yeah, you can't have too much plant growth at 100 millimeters. The next thing to check is whether your function is vectorized. So let's make a set of temperatures, and let's put that function in there, and let's maybe plot that temperature against the NPP of temperature at 1,000 millimeters of precipitation. Oh, okay. Well, that's at least it goes up. It's very simple, linear, and it hits a maximum. So apparently, rainfall becomes limiting. Let's see. Oh. Very high rainfall. Okay, so now rainfall doesn't limit anymore, but you do see at some point you know, there's a maximum you can reach. All right, so we could go on and on, but you know, most of the questions on Stack Overflow I see about this kind of use of a function that you want to apply to rasters is people that haven't looked at their function. Try your function first, and of course, the other big thing that you should never forget is put some NAs in there, 10 to 15. Very often functions fail for missing values. Well, here not. You have missing values, but it all works. Okay, so that's good. I like my function. Let's now apply to the rasters. So that's sort of new. In Terra, we have the app function, which was similar to calc in raster. And Terra has app. Terra has lap, which was similar to overlay in raster. And there are some others. There's rep for well, I won't even go in that. There's wrap, there's sap, there's all kinds of, you know, apply type functions that come in very handy. So let's run it. It already exists because I tried this out before. So I say overwrite is true. So know that I provide a file name argument here. You don't have to do that. Almost all functions you can give a file name argument. I often see people not do that and later want to write a file. If you want to go write a file anyway, then you might as well just do it in one step instead of in two. This message here is a nuisance that we can ignore. So we have NPP computed. There it is. Now this is not necessarily the same way as they computed NPP. But I thought it'd be I want to illustrate, you know, the use of lap, where we have two layers in this one object called clim, and they are used as the one layer is the first argument t, the other layer is the second argument. So the only thing you have to be sure about is that the order is right. Although you can also actually use the names if you want. You can match names to make sure that you don't have to worry about the order. All right, so now we have the NPP. Let's have a look at the data they used. which is available from PNAS, so that's nice. There's an HTML. I can download it and then read it. I simplify the data a little bit. I won't go into that, but well, what's important here, so now I have a data frame with their data that they used in their analysis. So they have the societies they talked about, the group that the societies belongs to, latitude and longitude of the location of this culture. And and some other variables they used in their model, and they have this, I added this moralizing, not moralizing. So with a data frame, with Terra, I can now make a I can make a spat vector. So we look at spat rasters, but spat rasters are created with the rust method. Spat vectors are created with the vect method. And so V is a spat vector, in this case of points, and it has all the data frame attributes in there as well. And we can add that to them. We can map that by itself. You get a little legend there, or we can of course put it on top of a let's do it again. An existing map. So now, okay, that's great. So we have reproduced some of their data, and I will say actually this paper is a great example that where by and large it's quite reproducible. I can't exactly get the same numbers, but I get very close. So I actually, so there was no trick there. There was no trick that I felt that they made actually one of these mistakes that are really overlooked, just purely a mistake in coding, a mistake in analysis, mixing up a variable, something that got sorted wrong. Nothing of that kind I discovered in this case. There's maybe the hardest part was to reproduce was this part here. After simultaneously accounting for potential non-independence among societies because of shared ancestry and cultural diffusion, we find, okay, so how do we account for this? And what does that mean? Essentially, it's Galton's problem. You find similarity between cultures, and you can attribute it to their environment, but it's actually more likely if they're near to each other, that is due to borrowing or to common descent. They're really sister cultures that have ancestor culture, if you like, which both have inherited from. Not even, we can come to that if there's time, but this whole question, well, how do you even delineate a culture? Where does a culture begin and where does it end? There's no, of course, there are no hard boundaries. It's very fuzzy. And so this is a general, very major issue, of course, in data in general. And essentially, you could say this is spatial autocorrelation, or spatial autocorrelation reflects this phenomenon. It also exists, of course, in all kinds of other data. It's just we don't have maps and we don't have the same tools to show that. Similarly, you could have it if you have data from 100 people, but it tend to be of the same family or so. There's all kinds of other ways in which independence is not guaranteed. But with spatial data, we actually have nice ways to look at that in other cases you don't have. And so this is what they did. So they said, we looked at the 10 nearest neighbor for a given observation as a covariate. So the first thing they said, well, okay, essentially what they're saying is like, well, I may have a moralizing high God, but if my 10 nearest neighbor also have that, that just doesn't then add so much weight to my, that point doesn't add too much weight to my inference because it's probably from borrowing. But if my neighbors are different, then it should be the important one. So this is how I implemented that. Terra has this nearby function. So I say, give me I can take this up first. So which are my which are the my proximate points, case 10. So for each point, what are the nearest points? I take out that first one because that's an ID, so we don't really need that. They're always ordered in the the sequence that the data came in anyway. So let's run this again. I make it a matrix in which I replace this number with its actual value. So let's see if we can look at that. So now for the first one, none of them has a moralizing high-God neighbor, but number 2 has 2 of them. And then that's the normal row means, oh, no row means, and I get a single value, and I can plot that. So yeah, this should not be surprising what we see now. We've already seen that, this was a phenomenon that occurred mostly in Europe, Northern Africa, and sort of the Near East, and so all these points only have, the 10 nearest points have the same values, whereas here you see a gradient, and here also, so Middle America, Central America is also kind of interesting, and here are some other gradients. So nothing surprising there, but it's always good to look at to see if what we did actually adds up. Finally, what we can do, we can look at the names of this vector, and we can write it to, in this case, I say, well, write a vector to a shapefile. Again, it already existed, so I'm going to overwrite it. On purpose, I take a shapefile here. It's a bit maligned, but still by far the most widely used file format, I think, for vector data. One of the real drawbacks of it, and maybe the main drawback, I think, is that if I now read this again, some of the names have changed. For example, so society name EA has been cut to society NA. It only takes 3, 6, 9, or 10 characters for a variable name. So be very careful with long variable names in shapefiles. Okay, so now we have, I'll call this, now we have prepared the data. We have the NPP data, we have the spatial autocorrelation, and I just, in interest of time and also of your attention span, I'm not going to reproduce all of the statistical analysis. I'll just show essentially what they did with some critique on it, and then 2 alternative ways to look at their data. And I have to reread it, but I could do it. I take the data frame from the spatial, from the spat vector, so essentially getting rid of the geometries. And I make a model. Moralizing is a function of abundance because I read it from the shapefile. It's a shorter file name. And, they did more complex models, but I'm just going to say, okay, their main finding was that moralizing gods, the presence of that depends on having a low NPP. We do, what was that? It was an error message. Okay, that's because I want to do GLM really. Hopla. Let's look at the summary. Well, for most intents and purposes, you can say, well, there's very strong support, right? The p-value is essentially 0. So in the simplest of worlds, you say, well, this is scientific evidence for this finding, and essentially that's what they report. They do a bit more, and they look at all kinds of other things, but essentially, like you say, well, you say that there's this association. One interesting thing I thought to look at is like, well, if this is true, if you I don't deny this correlation or this connection, or that this model fits that way. But if this were generally true, then you would expect that to happen, not only in this region, but also in the Americas, and maybe also in sort of, in the eastern part of the world. So how general is this really, or is this really something this is more specific, particular to this part of the world? So one simple way to look at that could be nice, an exploratory data analysis where I say, well, first I look at the relationship between the presence, NPP. Let me redo the figure here so that you see the labels NPP and the presence of moralizing God. And if you do that for all data, you see this relationship. So pretty strong. NPP, by the way, is here standardized so that, but this is still low and that is high. Now, if you only do Eurafrica, so between -20 and 65 longitude, including Southern Africa, we get a much stronger relationship, very strong in that part of the world. However, if we do only Southern Africa, there's nothing. Or the whole world except for Europe and Africa, there's also absolutely nothing, no relationship. That is surprising, particularly, for example, if you think of Southern Africa. Southern Africa is actually very similar to Northern Africa in the sense there's also a desert, there's also more humid areas, at least in the northern parts of it. So why would it be so different? What's going on here? Why do I think this is interesting? Now, we don't have really a setup to do Q&A here, but of course, it's a nice thing to discuss about in class. But and there's all kinds of alternative hypotheses you can think about, or alternative models you can propose. And I think that's really why I like this paper a lot, because it's one thing to say, well, yeah, we have this finding and it's all really interesting. And it's a whole other thing to say, well, does it add up? Does your domain knowledge support it? And then of course, domain knowledge is tricky here, especially because it's it's not only my domain anyway. I don't study the spread of religion. But one thing that struck me is that, and in their data, it's not so simple to see. But if you look at these cultures here, well, of course, the one thing is, gosh, there's so many more different cultures in some place in the world, another place in the world. Is that correct? Let's not go there for now. But another big thing is here, they took the culture as the point, the unit of observation, not the religion. And for better or worse, that could possibly make a huge difference. Because what do we actually see here? If you actually look, what religion do we have here? Well, we have Christianity and we have Islam, and there's Judaism in this as well. So in my view, you're really talking about one basic religion, Judaism, that is, that's sort of from which Christianity and Islam essentially derive. So you could also say, well, this is just really one religion here. And yeah, they took their 10 nearest neighbor, but if you think as one religion that is spread out, all of a sudden you have a very different process, and then attributing that that pattern to environment and rather than just a spreading event becomes a bit tenacious. Another thing I would point out is that if you think about Islam, currently at least, so the time aspect will be 0.2. It says 1700 or when is this? But currently, of course, Indonesia has the largest Muslim population, yet it only has represented by one, and Malaysia as well. So like 1, 2, 3, 4, 5, 6, 7, and then the southern Philippines, 8 points or so. Not very representative, and some of them are actually different religions. So not very representative in terms of numbers. So you can also maybe argue, well, maybe you should just weight by population. So there's all these alternative hypotheses that you could have and different ways you could look at these data. So I did one thing. Well, I already showed this. It really depends. I didn't show the p-values, but if you run the same model, with this very low zero p-value, essentially, you leave these data out, you get a p-value of 0.94, about as bad as you could get it. But you could also look at an alternative hypothesis, saying, well, let's just look at Jerusalem. If indeed I'm right, it's just a spread event out of Jerusalem, so that this is where Jerusalem is. We have this spat vector. I create a new empty raster from the average temperature. So by saying RAS-TF, I get a raster with the same structure as the average temperature data, but with no data. So that helps me often to rasterize things or to otherwise sort of create sort of new empty data sets, and I want to make sure that they align with the raster data I already have. That, by the way, is another common mistake people make when they work with raster data, and some of the commercial software sort of almost pushes you that way, is that they have make all these rasters that don't align. You know, the one thing that you want to do when you work with raster data is really, you know, from the outset, try to think, what is my area of interest? Make sure it's large enough. What is my my cell size or my pixel size? What is the origin? Make sure that, you know, typically try to keep your origin at 0, so that from there, you know, you can easily then make sure that all your other data that you bring in align. The other big thing is, you know, try not to reproject or resample your raster data, because there is always a quality loss. With vector data, you can do as much as you like. With raster data, you want to avoid that. So I created this empty raster, and rasterizes one point to it. I'm not sure if you can, oh, that actually takes a little while. It's funny because it's only one point, but well, as I said, not everything is faster, but there you go. So let's see if we can actually see it. It's very hard to see, it's too small. So let's compute the distance to Jerusalem. So the distance from this one point to all the NAs. And I'll use TF as to mask out everything that's, well, I can show it. What's going on here? Plot DGR. Okay, so this is distance from Jerusalem. It looks odd, but it's because at longitude and latitude data, you get these odd shapes. And mask with TF will then remove all the cells that are NA, or it will set to NA all the cells that are NA in the temperature data, so that helps us see better what's, you know, what we're dealing with. I can plot the points on top of it again, and I plot Jerusalem there twice for the white background, give it a bit of a halo, which seems appropriate here. So you see, well, you know, even by eyeballing it, you know, it's not the worst of a model. Where it doesn't seem to work very well is Southern Africa, because yeah, you're still not that far from Jerusalem, but there is this gradient here. So let's quickly, I'll just now do a model of distance. I have to do summary. And again, I see that you know, essentially 0 the effect. So it seems also a very good model. So we can, you know, of course compare them in different ways. So here I use AIC. Only distance and abundance, only distance and only abundance. So abundance again is an NPP here, and what we see is, well, the lowest AIC score is the best. So, you know, combined has most support if you use AIC. Separate, they're very similar, but actually distance is a better model than abundance. We can also do, you know, cross-validation with AIC. Well, actually, there's not cross-validation because I just used the testing data. We can also, but there's another measure, in which case, you know, the AUC gives a somewhat similar result. All right, so I got one left, but let's reflect a little bit more on that one. You know, and the big question becomes, all right, so why is NPP still useful? Well, because there's all these points here in more humid Africa where there are no moralizing gods, so that helps. I personally would take this model of distance a bit further. You know, I would claim, like, well, you know, think about how these relations were spread. They were actively spread both by Christians in the north and by Muslims in the south, but they were spread westward by relatively high population density peoples living in the Sahel. This more rainforest region was more isolated, lower population density, You can't have cows there. So there was this natural barrier. And so the question is, whether there clearly is this separation, but whether that is just because of, the people in the north just weren't interested in to conquer the south, essentially, or if there's different reasons, that remains a question, you can philosophize about a lot too, but you could also surely, if you take, for example, population density around maybe 1900, 1800 into account, you could also change that model quite a bit. Just one more last thing in R, and then I'll wrap up, and then I'll have time for questions. A whole other thing that I thought you might come up with, you could also do a spatial distribution model. Let's get bioclimatic variables. I thought I downloaded them, I guess not. So typically with the geodata, the way it works is a package, it will download the data once, but once it's downloaded to a particular folder, you won't have to download it again. And again, this is the reason I developed this. It's obviously to help reproducibility and just ease of writing a code. But one of the worst things always is having to deal with people's data. So if you want to share data in scripts, put it on a Dataverse or put it on some place on a Google Drive, or at least we can provide some kind of a link to it. Otherwise, it's just a mess. But then when you download it, I would also say make sure you actually save it, because it's here tomorrow. It's here today. It may be gone tomorrow. Anyhow, so filled that time. So now we have these bioclimatic variables that are often used in this kind of spatial distribution modeling or species distribution modeling, where essentially say, well, if I know the environments at locations of where I observe something, I should be able to predict where else that something could be or maybe is, or at least I can say where there are environments that are similar to where I've observed something. So the first thing I do, I extract from this raster, this SPAT raster bio values for these points V. So I had, bio has 19 layers. V has 583 points. So DME is 583 by 20, and that 20 is just because there's the first column is this ID. With points, there's not much relevance to it because it's always going to be 1-on-1. But if you had a polygon, you might have many values for a single polygon. So that's why that first column is there. I remove it here, remove the NAs. Random forest doesn't like it. Oh, I forgot something, I guess. Undefined columns order. Oh, problem. Do a random forest model. I always think of people think about machine learning as being difficult. And I always have to tell them, well, the machine learning part is very easy. In principle, one line, you're done. The hard part is getting your data in shape to be able to actually do this. And the other hard part, maybe actually thinking about what it all means and what it maybe doesn't mean. But given a model, we can make a prediction back, given mol M and the predictor variables that are in bio, make a prediction to where these moralizing gods may occur. Random forest is a bit of a slow predictor because all these complex trees. I should have made a smaller one perhaps, but there we go. Plot P and plot these moralizing gods. Now I think this is a really interesting result because on the face of it, you would say, "Oh, this is a great result." At the same time, it really shows also why this method is so weak. I feel. Yes, it's great because it really reproduces what we already do. But it also, while we're using environment as a predictive variable, there's clearly environments elsewhere that should be quite similar to this whole region, but it's all excluded. It's like, no, that's not similar enough, with very few exceptions because there were no blue points there. And so, these methods tend to be, unless you're very careful, and they tend to not be very general. They may be reasonable interpolation methods. They tend to be very poor extrapolation methods unless you take very good care. And so these were just some examples I gave. What else you might do with the data and how else you might think about it. And that was really my challenge for you. By the way, I'm trying to work this out in sort of a larger exercise that I'll put on our Spatial website, sometime later this year. So, I talked about, or I mentioned, most published research is wrong. That paper itself could be wrong, and that would be then a good thing, I suppose. There's also this problem of replication. Now, the context of this is actually more experimental replication. But I think there's still this big crisis of also analytical replication, even for those of us using R and scripts. And so I want to end with just a few comments about workflow design and what I do, and hopefully that is useful to some of you, and maybe you have some ideas or better ways that you can mention in a discussion. But I really want to emphasize it because as I the one thing that just keeps coming back when I work with graduate students and others is the the complexity of actually sharing workflows. So this is how you may have seen it already. This is how I make projects, how I organize codes. You may have seen that I already had, that if you paid good attention, that I had under my project folder, I had a data folder and a raw data folder. And always, download your raw data into a folder. Don't touch it with your hands, so to speak. Don't, use then scripts to clean your data. So that's your first scripts, data cleaning. And then maybe some final data sets that you actually use for analysis. Make other folders for graphs or docs or whatnot. Organize your code in separate files. Another real difficult thing is like you have these very long code files that are very hard, and somebody sends them like, oh, can you please help me? This doesn't work, line 350,000 line file. It's like, yeah, well, no, I can't help you really. Well, I actually try anyway. I don't know why, but I do. But the more you can separate steps out, the better. And what I should emphasize, that maybe this really sums it up a bit, is whenever you do a project, the more you start out thinking about other people needing to look at it and understand what you've done, the better. But that other person, and I'm old enough to have learned, is often your future self. So in this lovely cartoon, I always think of like, I'm asking, this to my past self, and yeah, so it took me a while, but in the long run, I'll have to solve, things will work, and here, this invisible person is running a system. To me, it's all about functions. What I keep hammering to my students on is like, well, you have to use functions. And as soon as I see somebody who actually starts writing functions, meaning not only making, putting code in separate files, but also now within these files, having clearly isolated functions that do a single task, like passing the salt, that's when their code becomes a joy to look at. And I would add to that, I actually explicitly said in my exercise, do not use the tidyverse. And the only reason for that is that I feel that that introduces all kinds of new interesting things. Maybe a lot of this is replication, but it clearly has cool features. But I see two downsides of it. One is actually sometimes very simple things in base are overlooked, so you get more complex code through the tidyverse. But the other thing, the extensive use of the pipe, or the McGritter, and whatever you call it in R, the pipe symbol has I think seems to stimulate long, complex pipe together workflows rather than much cleaner functions that are used in much shorter statements. So there's one very general point I want to make to all of you. Write functions, rush not. Thank you. That's my sort of whirlwinds where I try to talk about Terra in the context of reproducible research. And I hope that was of interest to at least some of you. Thank you very much for your attention.
Great, thanks a lot, Robert. So we're just in time that we have 5 minutes left for questions, and there are some posted on MetaMost.
Robert, can you turn on your video maybe, or is that an option? Great, thank you so much.
It works now, I think. I don't see myself, but maybe you do.
Yeah, we see you. Thank you so much.
There we go. Let me
thank you.
Zoom in here. All right.
Great talk. There's 5 minutes for questions. Please, Hannah.
Yeah, so the first question is about the extract function in Terra, because in the raster extract function, there was the option to have a buffer argument, which apparently is not there anymore for Terra. And the question is if this is going to come in the next version of Terra or not.
Are you sure? Let me check. It may not be there yet. I mean, so the answer, yeah, I didn't know that. If so, it's a really nice function and it should really come back. And if you don't see it, please send me an email or put it on GitHub so I don't forget. Of course, now you could make a buffer first and do that, but I agree, that's a nice function. Thank you.
Okay, so next one is from Etza. And
you're suggesting I ask it myself. Let me
you
look at
unmuted already, so I assumed you want to.
Oh no. Yeah. So the question is reproducibility. Using open source software for reproducible open science helps because users can try to read the source code to understand what is going on if needed. And then the question is, would our users being helped in that respect more by a package that's written mostly in R, like raster, or by a package that's mostly written in C++, like Terra?
Yeah, it's a good question. It's interesting. I mean, this is true. I think, though, that it's sort of at a very different level. I think most functions in a sort of a in a stable R package, you don't really have to, you don't really have to look at how the mask function works or so. You can see that it works. And so I'm much more concerned about sort of a more of an end user that doesn't have to. And how they can write better code with supposedly well-functioning R software, or whatever software you use. Mm-hmm. But nevertheless, it's of course so it is often touted as a great benefit of open source software, and it is true. I must say I've rarely used it, but particularly if something fails, I do it, or if I see that. A function doesn't quite do what I wanted to do, and it's like, oh, I'll grab Etzer's function and I'll add the thing to it. In that latter case, especially, I guess that for our users, an R function would be easier for sure. I mean, you can with RCPP, it's very easy to write your own C++ functions, but not everybody has that skill. So yes, short answer is yes.
Okay.
Okay, so the next one is a detailed technical one. Sometimes we need to plot a vector above a raster plot. This fails when the raster have many layers. How to fix this by just using Terra objects?
I didn't quite hear the first part.
Sometimes we need to plot a vector above a raster plot. This fails when the raster have many layers.
Oh, I see. So you want the same vector on many layers. So let's see if I can do that here very quickly. I'm not sure if I know at the top of my head, but you could do something like, I'll make a X is T. I'll just take the first 4 layers of T average to make it smaller, and then I would say plot X, and then there's a fun argument, and it should be something like function points V. Well, all right, I'll try one more time.
X didn't exist.
Oh, is that what it said? Oh, sorry. No, it's.
So T average is a single layer, probably.
Yeah, thank you. Oh, it's good that somebody's paying attention here. Thank you. Hopla. So we got now the full T average. Now 1 to 4. Hopla.
Right. So you have a function hook. Yeah. plot.
Yeah, so you can add a function that adds something to all maps. And actually, it's interesting. There's a feature request on GitHub where somebody said, "Well, could there be some way that you know on which layer you are, so that the function would have an argument, you know, layer or so, and then based on that layer, you could do actually something else." That's not there yet, but that might come.
For the sake of time, we have to stop now. The people